in this unit, we're going to look at applications of vectors. Now, this is not intended to be a physics course. I'm not going to try to teach you all the physics in that much of a way. Sorry about that. I had a little bit of a pause there. I'm not trying to teach you physics just all together in 2 weeks. That's not happening. But I am going to be teaching you selected topics that most effectively help you in preparing for future courses in this program, specifically related to a topic in engineering called statics. Statics is the study of forces and other phenomena on structures and how structures respond to those inputs. So we're going to look at forces a lot in this booklet, but first we're going to do a little bit of background in some other topic in physics called kinematics. So this booklet is divided into two parts. The first part is called kinematics. Kinematics comes from the Greek word kinesis or kinesis, which means motion. And so therefore we have the study of motion. And then we have the next half of the chapter, which is dynamics. And dynamics comes from another Greek word, which relates to the word force. So we have the study of forces. For those that have studied physics before, yes, you probably will know about 90% of this, but there will be some subtleties that you may not have seen before and some notation that is a bit more refined. For those that have not studied physics before, don't worry too much about it. I don't think that I'm going to do anything here that's profoundly too difficult. It's just keep in mind we're going to see how vectors ties into all this stuff. And as you know, for your evaluations, you can have your notes with you anyway. So if you don't remember a definition of something, you can always look it up. So that's about it. Look at these definitions here. We have position, displacement, and then we have a couple quantities, distance and speed, which are not vectors. You see how there's no arrow on top of them? And then you have velocity, and then you have acceleration. So these are all quantities related to motion. And what I want to do now is talk about each of these quantities individually, and then we're going to go and try some questions. I don't think that you're going to find this necessarily too dangerous, but it doesn't mean that we're going to go quick through it either. So we're going to spend the majority of today's lesson for the first hour on kinematics. That might spill over into the second hour. And then we're going to continue with a little bit of dynamics today, and we'll finish off the unit next week. So what I've done is I've written down this blank example page. And what I'd like you to do is by hand, if you have the paper in front of you or just on your tablet, I want you to fill in a definition for each of these, but you don't have to say it the way that I say it. I want you to think about how you could say it in your own words. So position is the first quantity that we have, and you can define it different ways, but I'll just show you the definition that I have in my notes. And these are on the cover of the booklet. So if you're not really sure what you want to say there, you could use my definition. My definition is not the best definition, but it's a definition that makes sense to me that I can share with you. So there's a couple of things going on here. Position, which is this quantity, most people will use the letter D, but also they might use the letter P. It really doesn't matter too much, the letter, but as long as you're consistent. It's a vector. So because it's a vector, we expect it to have a direction. So here's an example of a position, 4 kilometers north. So what's going on here? Well, position is a vector that describes where you are relative to somewhere else. So let's take a look. Imagine that there's a grid. So it's very useful to have some type of a reference or a grid, for example. So let's say that this is the reference point. I'll underline the reference point, and I'll just do that here, okay? Then if we're located, for example, here it says 4 kilometers north, then if this is north up here, then we're here. And the position vector would be this. So that arrow there represents our position on this coordinate system. Any questions about position as a definition? Who's never taken physics before? Who's never taken physics before and that makes sense to them? It's very quiet. Thank you, Joshua. We're a little light today. We got 25. We should be more around 40. So I'm relying on you disproportionately for more input, so thank you. So position, and we're going to use examples to clarify all these quantities. So after we do these 6 example definitions, I promise you several exercises where we can practice this. Displacement is different. Displacement, I want you to think about a journey. So when you go on a journey, there's a start and a finish. So when you go on a journey, there's a start and a finish. So let me show you an example of a position. Sorry, of a displacement. Let's say that here's the grid. And let's say that you start here and you finish here. Then that arrow there is your displacement. Not drawing a very straight line there, but that would be your displacement. So displacement is about the difference in 2 positions. Of all the quantities that I show you today, displacement and position, in my opinion, are the ones that are most often confused by people. So that's displacement. It's a vector that describes the change in position. Mathematically, you do remember the symbol delta because we used it in the calculus part of this course. Remember delta anything, think of like delta y. Back in grade 9 when you did slope, that'd be like y2 minus y1. It's a change. So whenever you have delta, it implies there's some type of a difference between a final and an initial quantity. I'll get rid of the delta y stuff because it doesn't really need to be there for this example. Here we have some final position and some initial position. Now for this example, I'm not putting any numbers here, but I promise you that I will put numbers soon once we get past these remaining definitions. Here's a big thing to contrast. Displacement versus distance. Fundamentally, they are very different. So distance is the easiest thing of all time. Distance is what you know from childhood. If I want to go from here to somewhere else, I would say, how far is it? And that's all you need to know. And you'd say, oh, it's so many meters or so many kilometers or whatever. So like yesterday, I went for a jog, and the jog was 4 kilometers. That's a distance. My jog was 4 kilometers. My displacement was something completely different. And we'll discuss what the displacement would be for something like going on a jog. Like if you leave your house and then you go for a jog and you come back home, then your displacement and your distance would be different. So distance is an easy one. Distance is just a scalar. The example I give here is 4 kilometers. Could be if you went for a run or a jog or whatever. Could represent your commute to work. If you're living downtown and it's under normal circumstances, maybe you live 4 kilometers from the college, so that's your distance to the college. A very common example for those that drive would know the odometer on your car, the device that measures how far your car has traveled. That measures distance for the car. So distance and displacement are very different, and we'll see examples, I promise you, very shortly where we differentiate and we compare the two. Now we have a couple of quantities that are very confused by people: velocity and speed. The big difference between velocity and speed is the vector on the velocity there. So velocity is a vector, whereas speed is a scalar. So I'm going to start with the definition of speed, because that's something, again, that, like distance, should be in your comfort zone. So there's speed. And these notes here that I'm giving you, don't worry, I'm not asking you to copy these down by hand. I will post these on Blackboard. Save your wrist energy until we start doing the examples if you prefer. In this case, you can see that speed is just what you know from a long time ago. It's distance over time. See, we have delta D over delta T. That speed is distance over time. So that's nothing different than what you learned probably in middle school. Speed is distance over time. But I'm not going to use this more primitive notation. I'm going to stick to this because I've already laid the foundation for notation here. I've called delta D distance, and I'm calling delta T, a time interval. You don't have to put those deltas there, and a lot of people that study physics don't put the deltas there either. I usually flip-flop on that depending on the situation. And for those that haven't studied physics, I'm not going to get into that, but usually if some people drop the delta symbol, it's because the reference point is 0. So you're subtracting 0 in this definition up here, for example, for displacement. In any case, this person or whatever is traveled 800 meters in 20 seconds. You divide the two quantities. And the key thing is that the units are still going to be units of distance per unit time. So in this case, it's meters per second. In the metric system, meters per second is the base unit for speed. It's not kilometers per hour. Those are derived. It's usually meters per second. And I don't have any imperial calculations here, but they may pop in the notes a little bit here and there. So just be a little bit aware that you might have to toss in a unit conversion from feet to meters. So nothing different than what you did in the previous course back in September. So speed is how fast your distance is changing, whereas velocity is how fast your displacement is changing. So velocity is also a rate of change. We spent a lot of time doing rate of change in the fall. So just remember, rate of change is can be thought of as a slope of a tangent on a graph. It can be thought of in an instantaneous sense. It can be thought of as a derivative. Although I'm not asking you to do any derivative calculations in this course. So velocity and speed do have similar units. See, here we have kilometers per hour, which is units of speed. But the big difference is that the numerator is a vector. So we have a direction that persists through the equation. So velocity is therefore a vector. The last quantity, and I'm not trying to gloss over these, I will come back to them again, is acceleration. So acceleration is the next layer on top of velocity. So let's say that your velocity was not the same. Let's say the velocity was not uniform or the same number all the time. Then the velocity, if it was changing, that's when you have acceleration. Now notice here that I was a little bit lazy with the vector. Notice that A here, I didn't put a vector symbol on it. There should be a vector symbol, and that is a typo. But sometimes A with a vector. That's what you'll see from different sources. Acceleration is a vector, but sometimes people get lazy and they don't put the vector because it's in one direction. When it's a one-dimensional type situation, people do get a little bit lazy by not putting the arrow. But you should have an arrow there. So that is a little typo on my slide. In the solutions, there is a vector on it, so I just need to correct that in my notes. Not a big deal. So anyway, enough of that. What I'd like to do now is spend some time philosophizing with you about these various definitions, and hopefully you can make sense of how they compare to each other. So here we go. You're not going to see any difficult calculations here today, at least with this early stuff. But let's start this first question here. So for those that have their calculators handy, feel free to tell me the answer in the chat. Once the answer's in the chat, I'll be safe to say that that we're good to go to the next step. So a car is traveling for 4.5 hours and it covers 361 kilometers. Find the average speed. So the word speed is relevant here. Speed, by definition, is distance over time. So what's the distance? 361. What's the time? Thank you. Thank you very much. Yep, and I'm going to go with 3 significant digits, so I'll go with 80.2. That's very good work. Thank you, guys. All right. So this question here is easy peasy. Whoops. It's supposed to be a happy face, but as you can see, my stylus is not behaving. Different question here. This is velocity. So what word did I insert here that is needed? Well, I put east here. See, when you want to find a velocity or an average velocity, you need to consider the direction. So average velocity is going to be what? Well, let's take a look here. Average velocity is the displacement over the time. Now, the displacement in this case is 189 kilometers, but in this case it's east, so you need to put a direction there. And the time here is a little bit unfortunate. It involves hours and minutes, so I'm just going to do this. I'm going to do 2, and I'll turn that into a decimal actually. I know that you can turn that into a decimal hopefully easy. I put a bar there because it repeats. Remember that you have a repeating decimal, you can put a bar on top. So 2, and if you take 38 and divide by 60, you're going to get 0.63. So if we divide these numbers, what do we get here? Anybody have a value for that? Yep. So I got 71.8, and the units are kilometers per hour. I might have to copy the solutions here. They seem like it's a little sluggish. Kilometers per hour east. So big difference between the two questions, but really it comes down to a direction. Now you might be like, oh, it's so easy. I just kind of like stick the east there, right? That's all you do. I guess that's all you do. But the next example is going to be a little bit more challenging. So these two examples, 4 and 5, are going to be a pair. They're like a package deal. Okay. So let's see if you can figure out the difference between examples 4 and 5. I'm going to just scroll it down a little bit. Okay, example 4. Before we start reading the question, I'm just going to go to the key word here, which is speed. And if you go to example 5, the key word is velocity. So in these two questions, we're looking to see what we're looking for what the net distance is in the first question, and in the second question we want the net or total displacement, and those are going to be different. Those are going to be different. Let's take a look how. So in the first example, we have 180 kilometers in 3 hours and 120 kilometers in 2 hours. So I don't think anybody would argue with me there that the total distance and the total time are these numbers here. So let me just drop those in. Let me know in the chat. Easy? Is that okay? Is that easy? Easy? Hopefully. Okay. Thank you, Barbara. So now that we have the distance and the time, Now we want to get the speed. So what's the final answer? Many of you can do that in your head. What's the answer there? Try to do it in your head. Yeah, that's right. And always make sure, don't forget your digits and your units. So in this case here, there's no issue of rounding. It is going to be an integral number of 60, and that's kilometers per hour. Example 5, though, is going to be profoundly different. Because now the notion of going east or west is relevant. See, over here we had east and west, but we didn't care about east and west here because with speed, these numbers just keep on adding up. Think of it like this. If you're driving in your car and you got to pay gas, right? You got to spend money on gas. If you went east and then you said west, then your car's not going to say, well, you only went, in essence, you only overall, you traveled 60 kilometers east, so I'll give you a discount on the gas. That makes no sense. Consumption, energy usage, it's cumulative, just like distance. So those numbers just keep on adding up. But when it comes to displacement's a little bit weird because the idea of easts and wests play a role. So I'm going to insert here my note, and I'm not asking you to copy this vigorously, but I'll just put it there. See that difference? In this case, we have a displacement which involves east and then west. So each leg of the journey is a different direction. So how would you add 180 kilometers east to 120 kilometers west? Well, the net result is going to be 60 kilometers east. If you're not sure how that works, I can assist you with one extra line of writing, and I'll do that right here because I suspect some people are scratching their head about that. So you see that there. Let me get rid of the 60 temporarily. You could probably do this, and it'll help you. You can say 180 kilometers east, like that. That's easy. What I'm going to do here is I'm going to take the west, and I'm going to turn it into an east. So that's going to become 120 kilometers east. But to accommodate that change in direction, I'm going to put a minus because the opposite of east is west. So that's how you deal with different directions with vectors, at least when they're one-dimensional, because east and west is a one-dimensional type behavior. So now we have the same things, right? This is like 180 minus 120 because all the units and directions are consistent. Then we can just say here 60 kilometers east. So hopefully that extra step there assisted you in understanding. Once we have those quantities, we can use the definition of velocity, or average velocity, which is to take the total displacement and divide it by the total time. So I will just put that up there in a second. So there's your final answer. So you can see here that the average velocity has a magnitude of 12. It's not 60. Because the velocity is telling us how fast the displacement is changing over time for the entire journey. And in this case, the entire journey, since you're going back on your own original direction, your overall change in position is not as much. Are there any questions? Let me know in the chat if you have any questions about this. Yes.
So to change from, you gave the example from 100 kilometers east and 120 west. So to change, we would have to take the first one. So why is not west? Why we don't transform from west?
Yeah. Well, what I did is I look at the larger number. So the larger number is 180. So if I'm going to switch signs on one of them, I want to switch signs on the smaller number because I want the overall sum to have a plus sign. I don't want to have any minus signs here. In theory, though, you could make the east into a west, And then over here at the end, you'd have negative 60 kilometers west. But negative of west would turn into east. So you'd be doing a little bit extra work at the end. But ultimately, whichever way you decide to flip these easts and wests, you'd get the same thing. It was a good question. So let's move on to question number 6. And again, we just have another question involving a speed. I thought I'd throw in a couple of questions here related to construction. So I have a crane and I have an elevator. These also will build just off of what we just discussed, so that's nice. So, what distance does a crane lift a weight if the speed is that and the time is that? So we have speed, distance, and time. So it's very similar to what we were doing before. Yeah, that's right, Saad. That's exactly right. I'm just going to get my answer there. There's a delay between me taking the screenshot and putting it on the screen. It's sometimes happens with my computer. So there's my solution. Let's walk it through it. So we know our formula is this: speed is distance over time. But in this case, we want to solve for distance, so that's why I've isolated it here. This means that we need to know speed and time. Thankfully, the speed and the time are right there. Oh shoot, I've copied it from the wrong question. My apologies. Just a second. So you can see here that it really is manipulating a scalar equation. And when you're manipulating scalar equations, nothing is out of sorts. We've dealt with more difficult scalar equations in the past than this. I mean, even in your building science course, like thermal conductivity, compared to thermal conductivity, this equation is nothing. This is not a big deal. It doesn't mean that I won't give you one this easy on the test. I'm just saying that it's supposed to be something fairly easy, that's all. In the next question, though, we do have something that I haven't introduced yet in terms of an example, which is acceleration. So acceleration involves a change in velocity. So in this case, we have an elevator whose velocity goes from a downward direction of and magnitude of 4.50 meters per second to a velocity that moves upwards at a rate of 2.56 meters per second. And this change occurs over a time interval of 2.43 seconds. So the formula for acceleration, if we go right back to the actual summary, I can just refer you here. It's this formula. See, A is delta V over delta T. Yeah, that's right. That's right, Saad. I'd put the V final first, okay? It's the final minus the initial, because change is always final minus initial. So I'm gonna just type this one out. I think it's worthy of a little bit of typing this time. So I'm just copying the equation that we had before. It's just in the cover there. So that's our starting point. And let's see if we can kind of decipher the question here. So delta t, I'm just going to copy it. It's 2.43 seconds. That's easy. But the numerator, we got to go like this. We got to go V2 like that. So V2 is the final and V1 is the initial. So once you have that, I think we're good. So the final velocity is the up one. So 2.56 meters per second up minus. There you go. I'll continue this on the next line. I usually would want to do one line of writing per step, but I don't have much room in this box here, so forgive me for that. Anyway, how the heck do we deal with this? We still have a situation where we have up and down. But in this case, if you're wondering, do I switch the up to a down or the down to the up? In reality, it doesn't matter what you do. But let me show you what the smartest play is. The smartest play is to get rid of the minus sign. That's the smart play. So turn that into a plus sign and switch this down into an up. And now I think it falls very naturally to finish the question. So if you take 2.56 and 4.50, you get 2.91. No, round it well, 706, sorry. Don't mind me, I like to think out loud when I'm doing my steps. Okay, so we have that. Oh, the numerical value here is going to be 2.91. Can someone offer us the direction? Sorry, not the direction, the units. What are the units here? What are the units for the final answer? Yes, the answer is actually Jai's answer. Nikita, the seconds build together. So the answer is meters per second squared. I'll clarify why that's the case, because that's often something that is confused. So I'll do that on the side here, okay? So we have meters per second, and I'm going to just do it like old school, like how you did it as a kid. 1 over second, sorry, divide by seconds. So then if you want to divide, you invert and multiply. So that becomes 1 over seconds. Sorry to go so slow through this, but I know that some people are going to appreciate this. So that's why I'm doing it. So that's why it's meters per second squared. Awesome. These are the little things that you're like, why? Who cares? But like, they're important. I want you to really understand a little bit further to the 2.91, okay? Just so this is just a little bit extra commentary. So when I write 2.91 meters per second squared, this is like saying 2.91 meters per second every second. That's what that's saying. It's saying every second that goes by, your velocity in magnitude is increasing by 2.91 meters per second. So that's what the elevator is experiencing. It's experiencing this. It's experiencing an acceleration or a velocity that's roughly 3 meters per second every second. Now that doesn't sound like much, but we want to compare that to something more natural, something more tangible in the world around us. So what I'd like to do now is discuss with you the quantity g. Who's heard of g before? I do not mean the alphabet. I mean physics, g. Who's never taken physics, but they've heard of like a fighter pilot or a roller coaster or whatever the heck it is, and they say, oh, that maneuver, that motion was like 5 Gs. G-force, yeah. F1 cars, exactly. So when an F1 car does a turn, they might do a 2G turn. So what does that mean? Well, I'll give you the quick version of it. I'll give you the quick version over here, okay? Objects in free fall at a rate, accelerate, sorry. Let me just simplify my writing here. At g equals 9.81 meters per second squared. And this is in the Earth, okay? This is in the Earth's atmosphere. Not on Mars, not on the moon. Different planets, different value for g. On the Earth, objects free fall at a rate of that acceleration. So in this question, we can represent our value of 2.91 meters per second squared as a fraction or a percentage of g. So this elevator, you can say, let's see how much it's doing. I mean, you can do this in your calculator in 2 seconds. What's 2.91 divided by 9.81? Hook me up with a number, somebody. What do we got? What does that equal? I'm trying to do it in my head. I got 0.3 something. Is it 0.30? Yeah, not bad. All right. I think it's closer to 0.3. I'm just trying to do the long division. Anyway, it's 0.3. So What does that mean? It means that the maneuver is 0.3 of g. So the answer is 0.3 g. So it's not, if you're thinking of it as a g-force, as Victor mentioned there, the 0.3 g is like saying you're experiencing a force which is 30% of what you weigh. So for example, if it was a 1g maneuver, you'd feel the extra weight of yourself. So like you feel twice as heavy temporarily. So 30% of g, it'd be like if let's just say that you weighed 100 pounds, then you feel an extra 30 pounds of force on you as the elevator does that change. Okay, I need to move it on a little bit because I feel I went a little bit too slow in the earlier stuff. And we do need to cover some two-dimensional behavior. So what I'm going to do now is 2 questions in 2 dimensions. And then after that, we'll take a break. And then we'll do as many questions as I can get to. My goal was to get to question number, I have it here. I wanted to get to example 23. I think it's realistic, but we do need to push it a little bit here. So what's different about question 9? In question 9, we have, let's see here, north and east. So you see how that changed it a little bit? We have an airplane which starts and it goes 573 kilometers north, and then it goes 297 kilometers east. So what the heck is it doing? Well, we can draw a grid here. And here's our reference point. So when you're talking about displacement, we need a reference point. Can someone tell me what the reference is in this question? What location is the reference? What's the reference? Anybody? It's very quiet. Yeah, it's Ottawa. Thank you, Ayo. It's Ottawa. See, everything that's being described here is as if Ottawa was the center of the universe. So here's Ottawa. I'll call it O. So first you go north, and then you go east. Now, I didn't draw a straight line there, but it's there. See, that's delta D1, and that's delta D2. So the question is asking for what is the overall displacement. So the question is asking for this vector here. So that's what our goal is. What is that delta D there? These vectors form what type of triangle? What kind of triangle is this? Yeah, it's a right triangle. So this is the easiest triangle to deal with, if I can draw it. And we do know some measurements on the triangle. So the height of the triangle here is 573, and the leg over here is 297. So you should be able to find this angle here. And you should be able to find the hypotenuse here, which I'm just going to call delta D, without the arrow, because it's just a magnitude here. Can someone do that for us, please? So use your Pythagorean and tan to do that. So what's delta D when you use the Pythagorean theorem? Yes, 645. Thank you again. That's 645 kilometers, okay? I think we've done enough Pythagorean theorems in our lives today by this point. Now theta, you can use tan theta. So tan inverse of 297 over 573. So what does theta equal? Anybody have a number there? I got 27. Can someone confirm 27.4? Thank you. So we have all the information that we need. We can write down the final answer here. So the displacement, it's 645 kilometers. And we can say here 27.4 degrees east of north. So this question, all I did really was go from east and west, like we did earlier, and I made it east and north. And you see how just having it with the north instead of a west, it makes the question a lot tougher because we have to deal with two-dimensional behavior. So there's only one layer that's more difficult than a right angle triangle, and that would be a level of difficulty where you have a general triangle, where it's not just east and north. Maybe it's a little bit more complicated because we have angles that are not 90 degrees in the triangle. So just take a gander here at question 10. We're going to go through question 10 and then we'll take our break. So here it says Toronto. Oh, I said it. I didn't say it like the Toronto way, even though I've been born and raised in Toronto. So my apologies. Let me say it like a tourist. Toronto is 650 kilometers at 19 degrees north of east from Chicago. And then Cincinnati is at some other position, because those are positions. Those are positions. What is the displacement of Cincinnati from Toronto? What the heck is going on here, right? So the first thing you want to do in this question is think about the reference point. So what's the reference point in this question? Anybody want to take a chance on that? What's the reference in this question? That's right, it's Chicago. So Chicago becomes the center of the universe in this question. Our initial position is Toronto, and our final position is Cincinnati. So there you have it. So we're trying to figure out the displacement from Toronto to Cincinnati. So I'm going to try to draw a picture here. It's not going to be the most glorious picture, but we'll do our best. And the perfect situation occurs here for motivating you why you don't want to have to draw the picture anyway. So it says here, here's Chicago. Toronto is north of east, so it's like over here somewhere. That's Toronto. And then Cincinnati is 390 south of east. Now 390 south of east is like maybe over here. You tell me in the chat, do you think my picture is okay? Do you think my picture is good enough to do what we need to do? Thanks, Barbara. I'm going to put TOR and then Sin, because Cincinnati is the same letter as Chicago, so it's a little bit confusing. So this is our initial position, and this is our final position. So that's D1 and D2. And the question is displacement. Displacement is going to be D2 minus D1. So if we could mathematically subtract D1 from D2, then we're done. We're done the question. And this is exactly the kind of stuff we were doing last time. Do you remember we did this stuff with the table? Remember the big table I made you fill in? That's exactly what we're going to do here. So we have, if we make a table here, This is not going to be very pleasant. I'm going to just insert it manually. So we need 3 columns and 4 rows. Don't worry, when I put this on YouTube later, I'll edit it all out. So we have here number 2, number 1, and then the difference. Then we have here x and y. So in the first case, D1 or D2 is, let's see, Cincinnati, right? So that's 390 kilometers. Can someone tell me what the angle is? What's the angle between 0 and 360? Remember how we talked about an angle between 0 and 360? 312. That is correct. 312 is correct. So for those of you that are wondering, where did this 312 come from? You need to go back to what we did last week. So we know that Cincinnati is 48 degrees. So this is 48 degrees here, south of east, but we don't want that number. Remember, we have to go all the way around like that. That's this angle right here. Whereas Toronto is easy. Toronto is super easy because that's 19 degrees. And 19 degrees is easy to play with. So we're just going to write that here. Toronto is, let's see, 650 kilometers and 19 degrees in the standard position. So we have enough information to get the x and y components. So if we do the x component, that's going to be 390 cos 312. Which becomes, confirm these numbers for me, because I did these this morning. Let me know in the chat if you agree with these numbers. Thank you, Jai. There's a formula for it, Barbara. The component goes, it's the component in the x direction for a vector is v cos theta. If the angle is in standard position, you have to go back to unit 10. This is basically unit 10. So the components are x and y like that. So 650 sine 19. So all the stuff that we did in the previous booklet, people, this is exactly, I'm just recycling the vector addition, vector components material. Now in this case, this is the first time that you're seeing an example where we're taking a difference. It's a difference this time. And the reason that it's a difference is because the formula for displacement is a minus sign. So every example I did with you last time in the previous booklet was about adding together, finding the sum. In this case, we wanted to do the difference because the formula here is position 2 minus position 1. So when you do that, you're going to get a negative here, negative 353.626. And over here, you're going to get a negative 501.446. So there you have it. I know that I'm dragging this on a little bit, and I know that you need a break, but we're almost done this question, and I think that you'll be very satisfied once we finish it. So there's our overall quantity in the x and y direction. So we know that we can reconstruct our final answer here. Let me just draw that vector here. So you can go east first or west. So we're gonna go, this is negative 353. Is that east or west? Is that east or west there? Anybody in the chat?
West.
Negative, thank you. That's a west. And I'll just put here 353. I'm not putting all the digits here if you don't mind. And then over here we have a south. So it's like over here, which is 501. I'm not putting the negative sign because the arrows indicate the direction. So what you have is an overall vector. Whoops. Let's just do it in red again. So there is the overall answer. See this vector here in red? That's our displacement vector. That's what we got to finish to do the question. So we need an angle here, and we need that. And just keep in mind, this vector that I drew here, because east is positive, Dogen, east is positive, in this case it's negative. And then in the y direction, north is positive, but in this case it's negative. Yes, there's a quiz today. Yes, there is a quiz today. Whoops. For those that want to answer this question with the sine and cosine law, you're more than welcome to, but I'm just doing it this way. What I want to show you is, see this red vector? That's this right here. What we just figured out is this. So it's nice that you can see that, because that's exactly what's fitting in the geometry here. So we can finish off the question now by doing inverse tan and Pythagorean theorem. So I'm just going to type that here. I'm not going to actually do the calculation because I need to give you guys a break. So find delta D. So if you do that, then delta D is going to become the following. So without the vector on it, it's just the magnitude. You should get 614 kilometers, and you're going to get theta. Eventually, you'll get 54.8. I'm confident with these numbers because I did these this morning and I checked them against my computer. I have a computer program that I use to check my work, and it was right there as well. So the final answer is this: delta D from Toronto to Cincinnati is going to be 614 kilometers, and then it's 54.8 degrees south of west. Okay, let's take a break. We'll take a break until 9:15. Yeah, Amir, I'll scroll back in a second. Okay, I'll scroll back and I just need to give some people time to take this one down. So yeah, let's resume class. Maybe 9:15 is too much. I think I need to cover quite a few little thingies here. Let's resume class at 9:10 or 9:12. I'm not being picky on the time here too much. So now we're going to look at a little bit of dynamics today, which is the study of forces. So what you're going to see is several examples involving finding the total or net force. Now, I said we're going to cover quite a few questions today, but don't worry because a lot of the questions are complementary. They're actually separate examples, but they work together. And I do think that you're going to find the material is going to be a lot more efficiently delivered in the second half. So the first thing we're going to do is focus on finding the resultant and equilibrant forces. So there's a lot of topics here. We're not covering them in order that you see them, but these are just kind of checking off a lot of boxes. So we're going to focus our attention to these two bullets here for the next batch of questions. So resultant force. You're going to be hearing the word resultant a lot in future courses. So resultant in physics with forces means the sum, the vector sum. So this symbol here, if you're not familiar with it, it just means sum. It means to total one or more, two or more vectors. So in this case, we have the sum of, well, you could have 3 vectors or 2 or 4 or whatever. I'm not going to go more than 4, I think, at least in this course. At that point, it just becomes monotonous. And the learning experience is really achieved when you do 3 forces anyway. So we're going to find the resultant force for some forces. And then we're going to find what's called the equilibrant force. And I'll discuss what that means through an example. It'll make a lot more sense that way. So let's take a look at example 12. I honestly don't think you're going to find these questions too hard. I'm not saying it delusionally. I do think you're going to find these questions like very easy. So here's two forces being applied to an object. The first force is 20.8. This unit here is kilonewtons. So I do try to expose you to different unit quantities for force. So in this case, we have kilonewtons of force, and the direction is to the east. Okay, that's good. The second force is 64.1 kilonewtons. Oh, look at that. It's also to the east. So when I want to find the resultant force, is it really that easy? What do you think the answer is? Let me know in the chat. What do you think the final answer is? Yeah, it is that easy. Anthony, yes. Yeah. Because they're both east. Let me show you my solution here. And it's not going to be the most difficult thing to follow, I promise you. I'm not going to just drop solutions on my screen here. But look at that. That's the answer, okay? Let's break it down. The first force, which I like to use the vector F, you should use the vector F for forces. You could also use P. P is a very common one in construction for a load or force. So anyway, the first force is 20.8 kilonewtons east. The second one is also east. Oh my goodness, what do you think? East and east means more east. So look at that. Let me know in the chat. Easy or not easy? Please say easy. All right, thank you, Barbara. So we got Anthony on board, we got Barbara on board, and then there's another 29 people that haven't, or 28 people that haven't commented. So I need to hear 5 more people tell me this is easy before I move on. Just a statistical sample size. Yes, east is easy. I got you there. That's hilarious. Okay, not easy. No. Oh no. Okay. All right. So it doesn't matter if you're dealing with forces or other quantities. The idea is that we have something of a force going to the east and a second one going to the east. So if you just add them together, then you're adding like terms. These are like terms. Let's draw a diagram of what's going on here. So I'm going to draw the object as a dot. Here's the dot, okay? Here's the first force, F1. And get used to drawing these pictures. And here's F2. Now F2 is longer than F1, so maybe I'll draw that as F2 and I'll draw F1 down here a little bit smaller. By the way, my friends, you do not have to draw a scale diagram in this course. I'm not going to ask you to draw scale diagrams. So that's what we're asking here, is that if there's a force here and a force there and they're both acting east, there's east, then the net force, which is what we have here, or the resultant if you want, is this. That's what you just calculated. Does the diagram assist you? I hope it does. I hope that makes it a little bit more meaningful to you. So there's a quantity here that I'm asking you for in question 13. For the previous example, so for this example we just did, it says state the equilibrant force. So that's the definition that I kind of glanced over, didn't really discuss with you. Yeah, Nikita, you went from not easy to the right answer. That is correct. That's the right answer. So let me give you a definition for equilibrant, okay? That's hilarious. Yeah, I have seen that definition somewhere in statistics as well. So that's equilibrant force, okay? It's the force that's required to neutralize, to offset, if you want, the other forces. So I'm going to draw the equilibrant force on this diagram. I just need another color, so bear with me while I search my little crayon set here. Let's go with equilibrant. Let's go with green. Okay, so here's the equilibrant force. Whoops, a little too thick for me. So I'm gonna do that. Okay, that's the equilibrant force, E. So E, or equilibrant, is negative of F. Got it? That's the formula. That's the formula that I presented to you in the notes. So let's put some calculations there, although you don't need to do any real intense calculations. The answer is in the chat already. I'm just waiting for my screenshot to appear. Oops, there we go. If you're wondering why there's a pause, when I take a screenshot, it takes about a 3-second delay sometimes. I don't know why. Sometimes it does, sometimes it doesn't. So anyway, there you go. That's the equilibrant force, and it's exactly what Nikita said there. Negative, see how I put a negative there? The negative of east turns into a west. So that first example, really, that they're companions to each other. We have a question that amounts to, I guess, nothing too dangerous, hopefully. But how does it pan out when you move to forces that are acting in different directions? And that's what we're going to explore through the next sequence of examples. So I'm going to scroll down to 14. It says here this time we have east and we have west. I mean, do you need to do algebra for this question? Can you just write stuff down? Yeah, really, honestly, people, all you need to do is draw a really cheap diagram. I'm going to answer this question with a picture, and I think that you'll get the gist of it. So the first force is east, and it's a shorter force. I'll just call that F1. And then the second force is way longer, and don't mind me with my lack of straight lines here. But oh, that's embarrassing. I'm usually good with taking responsibility, but that's not my fault. Okay, so anyway, we have the two forces F1 and F2. So let me ask you, who wins? Which force is bigger? Which force is bigger? F2. Can you tell me by how much, Jai? Yes, 43.3. So I'm going to subtract them. I did not use a single formula here. I drew some stuff, but I didn't use a formula. Because you don't need to use formulas for this stuff. You can visualize it. So that is the answer. That is the resultant force F. And the answer, let's just write the answer here with just pictures. Didn't do a single algebraic step here. So that'll be 43.3, whoops, 43.3 kilonewtons. And we're looking at west. So just switching the direction, you're seeing a similar pattern to what I did with the motion and the displacement stuff in the first half, where switching a direction from east to west profoundly changes the question. So here's example 14 with algebra, with a little bit more rigor in terms of what I present. While I'm just dropping a screenshot, you can think about question 15 if you like. There's my answer to 14. So again here, very similar to what we had in the first hour, we had an east and a west. We had an east and a west. Thank you, Nikita. It's just saving. Yeah, Anthony, it will become a minus. See over here? So Anthony was pointing out about something about a minus sign. So this is true. F1 and F2 is east and west. Now what you want to do here is you want to switch the sign. I think it's easier to switch the sign and make the east here a west. So I'll make it a minus sign. See what I did there? I made a minus sign. So now I have apples to apples. I have west and I have west. So I can have here negative 20 plus 64, which is positive 43.3. So this is not a correction. This is not an error. I'm just showing you how I fix it to do it in my head. And yes, and the next step here for sure, Nikita is correct. The equilibrant force is just the opposite of that. So that's what I was telling you, that in the second hour, the questions come in pairs. So for the first batch anyway. So yeah, that's negative 43.3 of west, which is 43.3 kilonewtons east. So now we have to deal with vectors that are not occurring in a straight line. And hopefully nothing too dangerous. So here we have a force that is east, but this time I made the second one north. I also changed the units here from kilonewtons to pounds. I want you to get used to different unit quantities. So this is pounds is a measure of force in terms of units. So we can clarify in this question that we have east and north. So this one's looking a little bit crusty, because we gotta go east and north here. So let me see what I do here. I'll do east this way. That's F1. But I'm not going to draw it like that. I know that you could do it like that. I'm going to do them tail to tip. Remember how I talked about that? How you can add vectors like a little journey there? So that is the resultant vector. And unfortunately, we have to suffer the consequences of the two-dimensional behavior here by doing Pythagorean theorem and tan. So we're going to need an angle here as well. So the magnitude of f, which when I write a magnitude, I just drop the vector symbol temporarily. The magnitude of f and the angle theta. Now, if I put some numbers here, the vertical leg of this triangle is 64.1. So I'll just put the numbers here. And the horizontal leg of the triangle is 20.8, with units of pounds, of course. So I did these calculations already. I'm just going to recycle my solution here, if you don't mind. See, this is the kind of stuff that you know how to do it, it's just annoying. You know how to do this, it's just annoying. Once you get the picture down, things are clear. So there you go. I did the Pythagorean theorem to get the force, and I used inverse tangent to find the angle. Once those quantities are there, then you can just write down the answer. See, we have the magnitude of 67.4 pounds, and we have a direction. In this case, it's 72 degrees, this angle. Remember that there is an implicit, it's understood that there's a north and east here. I'm using the standard notation and convention there. So we have a direction that is 72 degrees north of the east axis, so north of east. So that seems that we're really just doing a lot of the same mathematical background work. We're just decorating these questions a little bit different compared to the first hour. But that mathematical skill that you've been practicing for the past, well, this week, but also the past 2 weeks prior, is just that, just adding vectors together. That's all you're doing, people, is adding vectors together. Anybody want a gander to give a shot at the equilibrant force? What do you think the answer is for 17? That is correct, Jai. Yeah. Can I ask you, go back for a second? Let's go back for a second to the previous page here. Just for a second. So when you want to find the equilibrant force, see, remember the answer here was west for the resultant. Then the equilibrant, I just changed the west into an east. You see that? The west turned into an east. But all the numbers stayed the same. So Jai's answer is correct, but the most efficient answer based on that pattern, but Jai's mathematical answer is very rigorous. So if you want the explanation of why it works, it's in the chat. But the beautiful thing is that I can just change the words north and east to south and west and be done with it. And that will always be true. Whenever you have a vector quantity and you want to find the opposite of it, the negative of it, in this case, the negative means equilibrant because we're talking about forces. You just switch the number, you switch the direction. See, north becomes south and east becomes west. And it's so clean. It's so clean. That's like the cheapest answer of all time. The cheapest answer right there. No, Jai's answer is correct. Jai's answer is the same. It's just that Jai proved to us. No. Jai's answer is a proof. Jai proves to us why the answer is south of west. 72 south of west. And it's correct what you're writing as well, Asim. You're adding 180. You're adding 180 to this direction. If you're wondering why it's the case, the pattern really comes down to this. I'll do it in green. So there's the equilibrant force. I'll just circle it in green so that you know I'm referring to that. This angle here is also theta. See, they are opposite angles. So you're just leveraging the opposite angle theorem. That's why you're just switching words instead of numbers, because of the opposite angle theorem. Unfortunately, the next question, it just like layers up on this. So we're going to do question 18 together and 19 because they go in pairs. And then I'll leave you question 20 to try for homework. Basically, it's the same thing. So we're going to do 18 and 19 right now. But I'm going to use the component method because it really is frustrating to do these with sine and cosine law if you're going to do a lot of them. So anyway, question 18. Here we have two forces acting on an object. The first force is going 28 degrees north of east, and the second one's strictly going to the east. Why don't we draw a picture on the side here? So the first force is 28 north of east, so let's go over here. And the second force is going strictly to the east. So this is a very good opportunity for us to review the component method, although you could use the sine and cosine law for this question as well. So I'm going to go through the component method here by discussing the angles. So if we talk about an angle between 0 and 360, this angle is indeed just 28, and this angle down here would be 0 degrees because it's facing east. Remember, east is 0. So we could construct a table just like I did with you in the first hour and find the components of the force and work it through. The good news is I've already actually constructed this table in the solutions. So I'm going to walk you through that right now. So just bear with me while I screenshot it. Okay, so let's take a look at this table. There's our first vector, which is F1. So this index here, I, we did this in the previous booklet as well. We have two vectors. The first force has a magnitude of 20.8, and the angle in standard position is 28 degrees. The second force is 64.1, and the angle in standard position is 0 degrees. Remember, there was a formula for the x and y components. We actually referenced it in the first hour. I'll remind you here that Fix is Fi cos theta I, and then Fiy is Fi sine theta I. Just giving you a refresher about that from before. I'm using, in this case, it would be for this first box entry, it's 20.8 cos 28, second entry 20.8 sine 28, and then in this case 64 cos 0 and 64 sine 0. Notice that this entry here is indeed 0 because, of course it's 0 because the thing's going east. If it was going east, there should not be a north or south component to it. This first box here, this total here, refers to east and west, and this refers to north and south. So this answer here has a little bit of east and a little bit of north. So we can draw a diagram to show what's going on. So it's 82.465 east, and then it's 9.765 north. And these are units of pounds. And the resultant vector is over there. And the angle is required is theta. So we are going to do the reconstruction now. And I know that you do know that you have a quiz today. And this business of reconstructing the vector is definitely going to be on your quiz. So what you're seeing here in this box that I'm moving around, that really plays a role on your quiz today, as does the deconstruction, which played a role on your quizzes prior to the break. So we're going to use the Pythagorean theorem to reconstruct the force, and the inverse tangent to locate the angle there. In this case, it's a very shallow angle because the bottom leg of this triangle is, you can see here, it's much larger than the height. And you'll get a direction here which is north of east. So question 18 with the component method ends up with a reconstruction which is just as if it was like question number 16, which was strictly east and north originally. So it doesn't make it that much harder with the component method. What would be the equilibrant force for this answer? What's the answer for the equilibrant force? So that's questions 18 and 19. They go in pairs, as do questions 20 and 21. So I will ask you to do question 20. Whoops. Let's just keep it there for you to see the whole thing. I will ask you to do question 20 and 21 for homework, and I will post those answers on Blackboard. That concludes the forces, resultants, and equilibrium stuff that I want to talk about. So we do have another 10 or 15 minutes that I'd like to take, and then you'll have the third hour to work on your in-class assignment, which is a quiz labeled on your MyLab workspace. We're going to talk about Newton's laws for a little bit, but really we're just going to talk about specifically Newton's second law. So let me take a look here. I think actually, just give me a second, people. I'm going to just check something on my desktop. I might stop the class here, I think. Yeah. So we're actually not going to do any new material today. This is exactly, we're going to stop at this point. For those that want to invest some time practicing question number 20, I will leave you the last 10 or 15 minutes at this point to practice question 20, and I can put the answer up as well. So we're essentially done class for the lesson, but for those that want to do the extra practice, please stick around and try 20 at this point.